All right, welcome back to the deep dive. Today we're going to get into a challenge that, it affects almost everything, from cell networks to military bases. And that's the problem of timing. Specifically, how do you get a perfect GPS timing signal from an antenna to equipment that's miles away? We're doing a deep dive on the tech that solves this, the Thor broadcast H-4GPS-SMF system.
Right, and to even understand why this thing exists, you have to start with the basic physical problem. If you have any mission-critical gear, say a time receiver or some heavy-duty navigation sensors, it's basically on a leash.
A leash.
Yeah, a really short one. That equipment has to be installed within about 100 feet of the antenna itself.
100 feet. That's nothing if you're talking about a large facility or a military installation. And that's because of the cable, right? This standard RF coax cable just loses too much signal.
Exactly. The signal just degrades too quickly. So the core idea of the Thor system is actually pretty simple. It's a transmitter and receiver pair. It takes the GPS radio signal and, well, it turns it into light.
It turns it into light. Okay.
Then it sends that light over a fiber optic cable, and on the other end, it just turns it right back into a perfect radio signal.
Okay, so let's break that down. We're moving this super important timing signal from copper to fiber. What's the payoff? I mean, what kind of distance gain are we talking about here?
It's a massive extension.
Yeah.
I mean, it completely eliminates that 100-foot limit.
Yeah.
Using just standard single-mode fiber, this system can push the range between the antenna and the gear to over 20 miles.
20 miles. That is a game changer for anyone planning a large site. And I imagine the fiber itself is cheaper and just easier to handle than that heavy coax cable.
Oh, absolutely. The low-loss coax you'd need for this kind of thing is really expensive and it's bulky. Fiber optic cable is much less costly, it's way smaller, and it's just so much easier to run through existing conduits.
Okay, but if you're running a critical signal over 20 miles, you have to be thinking about interference. You're going past power lines, other transmitters. How do you keep that signal clean?
And that's really the beauty of using light. An optical signal isn't affected by radio waves at all. It's completely immune.
So you can run it through the noisiest electrical environments imaginable.
The absolute noisiest.
Hmm.
And the signal that comes out the other side is perfectly clean.
So it's immune to RF. What about bigger environmental hazards? I'm thinking about lightning. Antennas are usually in pretty exposed places.
That's a great point, and the system is built for that. Since the fiber itself is basically glass, it's non-conductive. It has dielectric properties. So if lightning hits the antenna, that electrical surge just stops. It can't travel down the line and fry your sensitive equipment.
That's a huge safety feature.
It is. And on top of that, the system has what they call a fiber security break. And you can order it with dual redundant power supplies. It's built for resilience.
And for those, really high-stakes setups, this specific model, the H-4GPS, provides up to 4 redundant links, right?
Exactly. 4 fully redundant GPS links. So if one signal path fails for any reason, you've got 3 others backing it up.
So all this brings us to who really uses this? Where does it make the biggest difference?
Well, it really comes down to critical infrastructure. The obvious users are places like broadcasting towers and, of course, military installations. But a huge one is cell sites.
For PCS synchronization.
Yeah, personal communication systems. It's how all the cell towers in a network stay perfectly in sync. It's what lets your phone call hand off seamlessly from one tower to the next. That requires sub-nanosecond accuracy. And this kind of 20-mile flexibility is, for them, an operational necessity.
And it solves problems on a smaller scale, too, right? Like on large ocean-going vessels.
It's the exact same problem, just shorter distances. You might not be going 20 miles, but you're trying to get a clean signal from a masthead down through decks of steel and incredibly noisy engine rooms to the navigation equipment. Fiber is perfect for that.
You also mentioned it can be used as a repeater.
In places where you just can't get a good PCS or GPS signal. Think about deep inside shopping malls or in tunnels and subways. This system can take a clean signal from an antenna outside and just pipe it reliably deep inside.
So to wrap this up, what we're really looking at is a technology that took a hard limit, a 100-foot tether, and turned it into 20 miles of flexibility, all while making the signal itself safer and more robust. It's sort of an essential tool for delivering time remotely and reliably.
And that kind of leaves you with a final thought, doesn't it? Just think about how many systems you rely on every single day, every mobile phone connection, every transaction that needs perfect sync. They all depend on this invisible backbone of reliable timing, delivered precisely where it needs to be, often with solutions just like this. It's the foundational infrastructure we never even see.